Welcome. Welcome to this talk on the upstream fish passage in Box Culvert, talk which was presented at Engineers Australia, Queensland Division in 2018. My name is Hubert Johnson, and I'm a professor in civil engineering at the University of Queensland. I would like to start by acknowledging a number of my co-workers and students. And here is the overall talk. So starting from the beginning, a culvert is a covered channel designed to pass water beneath an embankment. And from an hydraulic engineering perspective, the design is an optimization process, selecting the smallest barrel size, the narrowest part in the culvert, allowing for inlet control operation on the key design parameter as the design discharge on the maximum acceptable efflux, the efflux being the rise in upstream water level induced by the presence of the culvert. There are many kinds of culvert as illustrated on this photograph, but for the purpose of this talk, we shall focus on standard box culvert as seen on the bottom photograph. It has been recognized for the past 3 to 5 decades that culvert adversely impact on fish passage for a range of parameters, including excessive barrel velocity, the length of the culvert, insufficient depth, standing wave on the inlet and the outlet, debris, and all this being closely linked to the species and their swimming performances. Within the context of this talk, we shall focus on small body mass native fish species commonly found in Eastern Australia, with a total body length of less than 100 to 150 millimeters and a characteristic fish swimming speed from less than 0.3 to less than 0.6 meters per second. With a video here showing a small tubulate rainbow fish swimming against the current in a channel equipped with large bottom and sidewall roughness. Australia is characterized by a wide range of flow conditions and at design flow conditions. It is quite usual to have in the barrel some bulk velocity, cross-sectional adverse velocity, in excess of 1.5 to 1.24 meters per second, well in excess to the characteristic fish swimming speed of this small native fish species. So why is fish passage in the Australian culvert an issue? Because of the massive decline in freshwater population. And, for example, in the state of New South Wales, there are in excess of 6,000 waterway crossings considered as fish passage barrier. We could, of course, use overseas guidelines, but they are often developed for different hydrology on our different fish species. And currently, in 2021, we have Australian guidelines dating back from 2003 that are obsolete, ineffective, and no one will say. So let's think a little bit in terms of theoretical consideration, and let's think from the perspective of a fish. How hard is it to swim against the current? By analogy with sport physics. How much energy does a fish need to thrust itself in a culvert barrel? We may use Newton's law of motion, which states that the mass of the fish times its acceleration equals the sum of the force applied to the fish. And if we apply Newton's law of motion in the main flow direction, we obtain this relationship linking the acceleration of the fish to thrust, the drag, and the gravity force component in the flow direction. Acceleration, which can be derived from fish kinematic data, such as the one shown on the bottom here, showing the trajectory of a small fish in a channel, data recorded at high frequency. The drag force is proportional to the square of the relative fish swimming speed, and the power spent by the fish to thrust itself is basically proportional to the cube of the relative fish swimming speed. We can also calculate the energy spent by the moving fish by integrating the power spent by the fish. And typical data are shown here. This is a short record of about 100 seconds. In blue, we saw the instantaneous power spent by the fish based upon kinematic data on hydrodynamic data. And in red, we see the energy cumulative energy spent by the fish. And in this particular context, which is small fish, we see that the power exerted by the fish is of the order of 0.2 to 0.3 watt, with fairly substantial differences depending upon the fish is resting or sprinting. So some of the key outcomes of this basic consideration based upon classical sport physics suggest that fish will minimize their energy expenditure by swimming in low velocity zone because the rate of work is proportional to the cube of the velocity, and the energy spent is proportional to the cube of the velocity time, the transit time. We'll minimize sprint and drift. And simply, we may expect that fish may negotiate a culvert barrel on using local turbulence to follow continuous, interconnected, low velocity zones. These concepts are fundamental to weak swimming fish species, not just Australian fish species. Another theoretical consideration is based upon dimensional analysis. When we are looking at the hydrodynamics of a turbulent open channel flow, we can develop a relationship between the water depth, the velocity of the fluid, the pressure on the turbulent length scale as a function of the location X, Y, and Z within the channel, and the boundary condition, inflow condition, and fluid properties. This is limited, but that gives us a general idea. On using the Pi-Buckingham theorem, we can derive in dimensionless form a relationship between the dimensionless flow properties as a function of the dimensionless location and a number of key dimensionless numbers, among which one may recognize a Froude number, Reynolds number, and Morton number. In practice, open channel flow, including culvert hydraulics, would be modeled using a Froude similitude, implying that in the model, the Reynolds number will be much less than in overlap, especially when we are dealing with small or very small physical models. We may do a similar reasoning in terms of the fish swimming by linking the fish swimming speed, the fish swimming speed fluctuation, oxygen consumption, and response time of the fish as a function of the location, fish characteristics, boundary condition, turbulent flow, and fluid properties. On using the Pi-Buckingham theorem, we obtain a series of dimensionless relationships showing in particular some key parameters such as the ratio of the turbulent length scale to fish length scale, as well as the species. Altogether, it is nearly impossible to fulfill dynamic similarity on identical dimensionless number unless working at full scale or near full scale. And this means that any physical modeling has to be undertaken at near full scale characteristic to be relevant to real world events. So, in summary, small scale physical modeling is meaningless. We need to use large, sound physical modeling at near full scale, and we need also field work. In terms of modeling, we can conduct some physical modeling, and we have done so in some 12-meter long, 0.5 meter wide channel, which is near full scale, with different type of boundary conditions, ranging from smooth channel to rough channel on triangular corner baffle, small triangular corner baffle, with a detailed amount of hydrodynamic measurements, including velocity and turbulence measurement using Cornell pitot tube, Preston tube, and acoustic Doppler velocimeters. We have, in addition, performed some kinematic record of the number of fish motion using two fish populations, juvenile silverfish perch and Dubulier rainbow fish, and using high-speed video, 240 frames per second, we are able to get a large amount of information on fish kinematics. An example is shown here. We are looking here at a small Dubulier rainbow fish, as seen in the video, swimming against the main current. The video is a 1/8 speed replay. The graph here shows in blue the fluid velocity fluctuation, that is a histogram of fluid velocity recorded at high frequency, 200 Hz, in blue, while in red, we show the fluctuation or the histogram of fish speed. And what we find is that basically the fish speed fluctuation are much less than the fluid velocity fluctuation at the same location under the same condition. And altogether, for a range of fish and a range of flow conditions, we can obtain some experimental data showing the ratio of the fish speed fluctuation to fluid velocity standard deviation, typically much less than 1 for two different species and a number of individuals for each of the species. We can similarly look at the autocorrelation time scale, that is the ratio of the fish response time to the turbulent time scale. And interestingly, we find them two correct approaches. We can find here two characteristic values above unity or less than unity. We can continue to look at the fish swimming frequency. Typically, we find expression as a function of the fish length, showing that basically there's a very close correlation between the tail bit of the fish on the two species. Now, another form of modeling is doing numerical modeling, namely computational fluid dynamics modeling. There we use a commercial code, and depending upon the type of boundary condition, you use different numerical approach. Reynolds average Navier-Stokes equation to larger dissimulation or more complex geometry. Importantly, any numerical modeling required a solid validation, which implies detailed validation data sets. Based upon our own experimental data, we have been able to get some good agreement in terms of the free surface observation, but we find that the CFD numerical models are extremely sensitive in terms of the velocity field, sensitive to the grid, to the turbulence model, and overall to the settings. When properly validated, CFD can provide a large amount of information and can provide information on comparative performance of different conditions, and can provide insight in what we can expect in terms of fish behavior, like here, this juvenile silver perch, swimming in the bottom corner of a channel, trying to find shelter from the high velocity. Other example of results are shown here. On this graph, we show the flow past small triangular corner baffles. The dark blue area are low velocity zone. And we see in particular that for the small baffles, the smallest baffles, there is a lack of continuity, interconnection between low velocity zone, which will adversely impact upstream fish swimming. So moving forward to developing guidelines, we have here a conundrum. On one side, we want to minimize the barrel size in terms of the hydraulic design to minimize the cost of the cuvette, but biological requirement suggests that we need to have much lower velocity in the barrel. Some of the challenge is that on one hand, we have some biological data, which provide very good information on the fish behavior, on some characteristic fish swimming speed, but this test is usually conducted in very small facility, often with a lack of standardization of the test method. They are often single point velocity, which do not provide a complete velocity field, and sometimes there are issues with the accuracy of the measurement. On the other hand, hydraulic modeling provides very detailed information on the velocity field based upon advanced physics-based theory, but this traditional hydraulic modeling do not provide information on the fish behavior. So what can we do about it? We can spend a lot of money. That's what's happened in this bottom structure, a culvert that has been retrofitted for a cost of nearly $120,000 with a reduction in discharge capacity. Or we can try to tackle the head-on the challenge by bringing together biology and engineering rather than biology versus engineering. And there, professional engineers have to be much more proactive. So we need engineering guidelines for fish-friendly cuvettes that are simple, realistic, politically acceptable and publicly acceptable, and meet engineering standards. We propose here a different design approach, one where we will focus on flood passage at high flow and fish passage at lesser flow. The bottom graph shows a typical hydrograph of flood in a cuvette. And we propose to focus on the fact that fish will swim as soon as there is some water. And if we could maximize the condition for fish swimming in most of the time, we may hopefully have achieved some successful design. So we need to adapt our design. One option is to set a threshold in discharge below which we focus on fish passage and above which we focus on flood capacity. Another approach is to look in terms of the duration of the flood event. Altogether, both approaches tend to yield similar outcome, especially in terms of the Australian hydrology. And then we need to match fish swimming performance on hydrodynamics. The small graph in front of you shows some information on the fish behavior in a channel with a rough sidewall, a smooth sidewall on a rough bed. And we find that irrespective of the boundary condition that we tested, fish swim preferentially next to the sidewall and in the bottom corners. Hydrodynamics can provide us detailed information in this region, in this low velocity zone. And we propose here in terms of the design to match the swimming speed with the characteristic on the side of the low velocity zone. Physical observation, like this one, the bottom graph showing the velocity map in a channel equipped with bottom triangular baffles that are highlighted with dashed black lines, enable us to calculate very accurately the size of the low velocity zone. And for example, for the same flow condition, in a smooth channel, we will have low velocity zone of about 7% of the cross-section area. When we have a rough bottom on a rough wall on one side, we can get about 17% of the cross-section area corresponding to low velocity zone. And when we use small triangular corner baffles, we are able to achieve between 10 to 25% of the cross-section area being characterized by low velocity zone. So some of the key outcomes is that current guidelines in Australia are obsolete. We propose a design optimization in terms of flood passage at less than design flow and flood capacity at design flow condition, focusing on providing low velocity zone. This approach is valid not only for smooth box culvert, but other geometry. So in conclusion, culverts on flood are not new, but the development of cost-effective, fish-friendly culvert design adapted to small body fish species is a major trend. Theoretical consideration emphasize that the fish will spend power at the rate of the cube of the velocity in swimming against the current, so it will seek low velocity zone. Dimensional analysis emphasize the complexity of fluid-fish interactions. We can use both laboratory and numerical model, and we believe that the future will be hybrid modeling combining both physical and numerical experiments, provided that the latter are properly validated. We propose new design guidelines that are focused on the fact that fish swim every time there is some water in the culvert. Keeping in mind that this fish, especially small fish, will swim preferentially next to the wall on the bottom corners, with a design optimization for fish passage at less than design flow and flood capacity for large discharge near design flow condition, by matching fish swimming performance to low velocity. We need to be more proactive, and there's an urgent need for new engineering guidelines for fish-friendly standard box culverts. Here are some bibliography. Further bibliography here. Thank you very much.